How's everyone doing today? Nice, nice. I heard it's just going to get actually much bluster. By the time we leave here, it's going to get, well, Nicole's saying overnight, maybe by the time we leave back down to 20 degrees. So, hope everyone didn't wear their spring jackets. Yeah, you're screwed. Right? Got another layer? All right. Well, hopefully you'll survive. All right. So, before we get into all the other meat, the first thing we always do, our grand tradition here, who is hiring? Is anyone looking to hire somebody? All right. Come up, tell us about the job.
So I'm Kevin Macbeth. I am hiring for a business intelligence person. We mainly work with Power BI. My team builds the rating engine, so the things that calculate the premiums at Arch Insurance Company. You can go to Arch Insurance. The requisition number is R25_215, or you can find my LinkedIn profile by just going to actuarialhero.com.
Nice. I like that domain. Can you post it in the Slack?
Yeah.
All right. For those of you that don't know, we have a Slack. You go to nyhackr.org and you could click the little hashtag for the Slack. There's a channel called Job Postings where people post jobs there, and you can go apply for the job if you want a job. Cool. So thank you for hiring. Is anyone else hiring or looking to hire people? I guess that's the same thing, but no one? All right. All right. Done hiring. All right. So then, on to more optimistic things. The pizza is from Pizza d'Italia. Did I get that right? Pizza d'Italia. So my regulars, you already know what to do. All the new folks, pull out your phones and go to bit.ly/pizzapoll, all lowercase, and vote on the pizza on a 5-point scale. Those who are regulars know we've been doing this for 12 years or so, 13 years, hard to keep track. You can keep track of this pizza, so go on there, let us know how the pizza is. All you folks at home, I know you are not eating pizza with us, but maybe you're eating pizza. Maybe you're having dumplings or tacos or bread or soup or whatever. So if you're at home and you're eating and you want to share what you're eating, you have two ways to interact with us. You can either comment right in the comments of the YouTube live stream, let us know what you're eating, and we love seeing it. Or in that same Slack I just mentioned, there's a channel called Monthly Meetup Chat. Go in there, tell us what you're eating. If Jeff Ryan, if you're there having a deep dish out in Chicago, let us know. If anyone's in New Haven having that Amalfi Coast style pizza, let us know, and we will enjoy it. Or if you're having non-pizza, let us know too. All right? So, folks, chime in. Next month, in May, we are going to have Donnie Greenberg talking about AI orchestration. So that'll be a nice, fun talk. The details will be posted in the next coming days or weeks, but that's all scheduled for May. I think we have June's person lined up for June. All right, we need a June speaker. Who here is going to be a June speaker? I can call on people randomly, and that has worked in the past. It really has, Kevin. No, you said all right. You heard that. All right, Nicole, he's doing it. All right, Kevin's giving a talk. See how easy that was? All right, do we have July yet?
No.
All right, who wants to do July? Here's your chance. We like planning these things in advance. Makes things easier. Oh, you said you'd give a talk a while ago, didn't you? Yeah. When you're not chewing, we'll talk to you about that, okay? All right, but we need some more speakers to fill out the rest of the summer because we like to have some things planned a little bit in advance. We have June. Thank you very much. And if anyone at home is watching and it's going to be in New York and wants to give a talk, let us know. If you know you're going to be here in like 3 months, you're going to be passing through, we can arrange to have the meetup when you're in town. We do this all the time. People visit from other parts of the country or from abroad, and they give a talk when they're in town. So let us know if you're visiting and want to give a talk. We'd love to have you. After the talk tonight, we are going to go to the bar. We're going to go to Malt House. It's been good so far, I think. Does everyone enjoy Malt House who's been coming? Yeah? All right. Show of hands because we'd like to let them know we're coming. Who's coming to Malt House? Raise your hand. All right. You got a good rough head count? All right. Cool. Paul, you didn't raise your hand. Paul. You're a veteran. You know that you're, all right, anyway. So, and folks, by the way, just because you're going to the bar, if you don't drink alcohol, that's cool. Come have a non-alcoholic beverage. Have a snack. Just chat, hang out, have a good time. It's really fun just going out to the bar and just talking to everybody. We might talk more about this excellent talk. That's going to be one of the best you've ever seen. Or you might just talk about, why are they all laughing? Or it might just be fun to chat with your friends about life, movies, sports, all right? So just come hang out with us. It's a really good time. We would like to thank George, who is not here right now, but George is the person who gets a space every month from NYU. Thank NYU, of course, but George is our conduit. So a round of applause for George, who will not hear it, but maybe we'll see the video. He's been crucial in us getting space here, so we're really, really thankful to him. And if you see him next time, you can't miss him. He's like this tall. Give him a thank you. Give him a good handshake and tell him thank you, because it's really helpful having the community participation here and being able to have this beautiful space for everyone. All right. I think that is everything I'm supposed to cover. We don't have any stickers tonight. We need to get more stickers and put them out. Are we out of them?
I think they're in my box.
Okay. All right. Well, next time we'll bring stickers. All right. All right. So with that, I am very excited to introduce our next speaker. I met him 2 years ago on the lunch line, and he's wearing a math t-shirt. So I immediately said, oh, you like math? Come to this group. And this is how we get people to speak, right? And he's been coming for a little while now, and this is his first talk. So we are very excited for this very nerdy talk coming. Thank you very much, Garo.
All right, thanks, Jared. Thank you for everybody being here, and let's just dive right into it. I'll try not to make it too nerdy, I guess. If I'm a math person, and if I get too mathy or also too teachery, please just stop me, be like, hey, reel it in. You're getting too mathy, okay? So, quotes from goats. Let's start off with some of the goats. First one is really a collection of goats, and that's Mike Francesa's Callers. First time, long time, like Jared said, this is my first time speaking, but I've been coming for over a year now, and it's a pleasure having this opportunity. And so given that, I do want to give a thank you to the organizing team. It's great to see all the work that they put in behind the scenes. I show up early, and they did all this AV stuff that I've never done before, and super cool. So let's give them another hand. Thank you so much for organizing this. All right, our next GOAT is John von Neumann. And so he said, young man in math, you don't understand things, you just get used to them. And I think this is a sentiment that a lot of people have felt before, including some of my students who are watching when I'm speaking, like this morning. We've all felt this in a math class. Myself, maybe more than anyone else, because I've taken a lot of math classes, and I'm just sitting in the back like, I don't understand what's going on. And so you really just have to put your head down and do it, and like study, 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 and then you get the sense of it. And it helps to work through some examples, and so that's what I want to do today. So this being a Stats E conference and me being a number theorist, I thought the intersection of these two things would be something in the probability theory world. So there's this really cool theorem out there called the Erdős-Katz theorem. So Erdős is this number theorist, and then Katz is this probability theorist. And it has to do with counting the number of prime divisors of n, which on average is log of n. And so that's the average, but this doesn't just tell us what the average is, it tells us what the full distribution is. And it says that if you allow x to get bigger and bigger, and you're counting how many average prime, or how many prime divisors n has, it actually has the normal distribution. Okay, so it follows this Gaussian. This might be my favorite theorem. And so I wanted to walk through the proof of this because I didn't fully understand it, and it's good to try to understand. Okay, so the good news is there's a great exposition of this in Gerard Tenenbaum's book. So we'll look through that. The maybe not so good news is that this is in French. But there's enough math to give us like steps to get from one step to the other. So von Neumann was talking about characteristic functions, which confuses most people. And this example of the use of characteristic functions, which you could see la fonction, caractéristique, correspondait, soit, that's the characteristic functions that's used in this proof. Okay, so I'll give you all a second to digest that before we dive into the proof. Okay, I'm just messing with y'all. Like, we're not, I feel like y'all could tell, like, it was not that obvious that, it was pretty obvious that we're not going to talk about the Erdős-Katz theorem. Imagine if we did, though. So, that would be great. Okay, our third GOAT. Richard Feynman. So he says if you can't explain something to a first-year student, then you don't understand it that well. So part of this, the motivation of this talk is I struggled in linear algebra over 10 years ago. and I'm trying to learn graph theory, so I wanted to do a few projects. This was a forcing function. Jared's been like, give a talk, give a talk, give a talk. I finally came up with this idea. I was like, okay, I'll give a talk on this, and it'll help me understand it, and maybe I could teach y'all some of the stuff that I understood. So all that being said, more motivation. That was the first fold motivation. The second fold motivation is ever since I started teaching, there's this issue that's really been bugging me, and it has to do with fairness. And like, I deadass think that it's because, pardon the French, but I think it's because I'm a middle child and I want things to be fair. So there's a secret. So, sorry, I have to give a bonus point to my students who are watching. Sorry about this. The secret is you could learn things by teaching. Okay, that's the secret within teaching. You learn things by trying to explain it. That's Feynman's method. But the thing that's been bothering me is fairness when it comes to grading. So in colleges across the country, there's 1,000-person Calc 1 classes, right? Like you probably sat in a Calc 1 class when you were a freshman. And when it came time for exams, all the TAs and professors would get together and they would grade. And not every professor is going to grade, or every TA is going to grade every student. And the students might be like, oh, is this fair? You have some sort of bias. Like, what if your test happened to be handed to the one TA who's really, really mean, or to the one who's the candy man and is giving you like really high scores? And so there's a little bit of bias introduced in there. And we see a similar example maybe in the pizza poll. So I want to walk through this pizza poll as just like a motivating example. This is hypothetical data because the data online is summary statistics. Otherwise, I would have taken actual data. And so you might be able to extract some patterns from this. So 1 being the best rating, 1 is the worst rating, 5 is the best. And so we go through a few lines. We notice a few things like Chris and Adrian maybe have similar ratings for things. So shout out to everybody on this list for participating in this hypothetical poll. Who else? We have Eric. Welcome, Eric. Francesa. Mike Francesa is really mean when it comes to rating things. And you don't want him grading your exams because he's going to give you low scores. And on the flip side, maybe I'm just very generous. I'm just giving out high scores. And so you see this problem in a lot of places, whether it's the pizza poll or it's exams, or I have a few other examples here. So when it comes to Uber ratings, right, you have drivers and passengers rating each other, and maybe Mike Francesa is in a car and he's giving out 1 stars to people and lowering their averages, or maybe he's driving the Uber. And same with Airbnb hosts and guests. You could have this at a more aggregate level. So you could have, say, college admissions are trying to decide, should we take this student from this high school that's really good, but the student's like middle of the pack, or should we take this valedictorian from a school that we haven't had students from? Or on the next level, you could see it, are we going to hire the person with a 3.9 GPA from the school that is notorious for grade inflation, or are we going to take the 3.5 student from the really, really difficult school? So you see a lot of examples of this in everyday life. I think it's one of those things that once you see it, you can't stop seeing it everywhere. Okay. So another example that we're going to use just as a medium to go through some of the ways to try to analyze what the averages are and what the true ratings are is through sports, because sports has a lot of data, it's readily accessible, and I have some domain knowledge with respect to it. So we're mostly going to walk through it with sports, and then we'll do a few other graph theoretic examples with music. But you could keep in your mind whatever your favorite example of this is, and think about how the methods we're going to use will apply there. And so I guess one more question before we dive into the sports. So we just went to La Pizza Italia, and Francesa and Eric both showed up. And now the question is, like, which of these pizza places is the best? And so maybe you want to go based off of average score. I don't know if that's the best metric. John's has a pretty high average score, but also Francesa didn't go there. LPI has a 3.5, but Francesa was pretty generous there, so maybe it's better. And it's just something to think about. So how do we figure out who has the best pizza given this incomplete rankings? Okay, cool. So given all that motivation, let's dive into sports. So the sport of choice, it being last night being the championship, March Madness. So this is similar where you don't have every team playing each other like you do in some other sports. Like in professional sports, most of the time you're going to have every team plays each other, and so you have a good sense of who's better than who. But in college basketball or most college sports, there's just too many teams for everyone to play each other. So we're going to deal with this past season, 2024-2025 data. There's over 6,000 games. I cut off teams that didn't beat any other D1 teams because I just wanted to throw them out. They would mess up some of the analyses. So we're left with 35 teams, and they're organized in 31 conferences. Okay, so if you do a little bit of number theory, you could maybe compute there's about 35 games per team, and they're also organized where they play their conference teams a little bit more than they play the non-conference teams. Okay, so you sort of have this clustering where within a conference you could see who's better than who, but then how do you compare teams between different conferences who might not have played each other? Okay, so at the end of the season, March Madness, which just finished last night, we have this big tournament which does decide a final winner. It's nice that the best team will bubble up to the top and win it all, but we also have to figure out who plays who in the earlier rounds, because you want the best teams on the opposite side of the bracket so that they play each other in the championship. You don't want them playing each other early on and having like a less watched game be a really good game. Okay, it's single elimination, 63 games. I put an asterisk because if you're a pedant, you'll be like, oh, there's more than that many teams, but whatever. At least one team from each conference, and so there's a committee who does the rankings. Okay, so they look at these 6,000 games and they determine who is the best seed, who's the next best seed, and so on and so forth. And they do all this seeding. It's a really big event that people like to get excited about. And so we're going to try to do that. I don't know how good everyone's ball knowledge is. I don't really watch college basketball like that, so I don't have that much domain knowledge. But we have some stats, some linear algebra, so we could do this. Cool. And with any good project, we're going to have some sort of benchmark. And so I'm going to treat the pre-tournament games, all the games leading up to the tournament, as the training data, and then you could use the tournament as the test data, where I'll just say if Team A is ranked higher than Team B, then Team A will win that game, and so on. Okay? And we will test against how did we do compared to the NCAA committee's rankings. I know they have other factors that they have to consider, like they don't want two teams from the same conference playing each other early on, so like I give them credit. They have a very difficult job. But we're going to do it ignoring all those other constraints. Cool. So here's our 64-team bracket. It's hard to see everything, so I want to zoom into this region in the bottom right to these 6 teams. So we have Illinois, Xavier, Kentucky, Troy, UCLA, Utah State. They all have similar records, but if you look really closely, you could see the lower seeded team, which is the higher number, so that 11, Xavier is perceived by the committee to be worse than Illinois despite having a better record, right? They won one more game, they lost one less game. So they had a better record, but the committee said Illinois was better. And then same with Kentucky and Troy. Kentucky had a worse record than Troy, but they were seeded much higher, a 3 seed versus a 14 seed. And then same with UCLA and Utah State. And the committee got it right. Like these 3 are the scores, and they were actually blowouts. So how did the committee know this? Like what's the idea here? And if you do know ball, like maybe you're like Kyle and you're like, I really know ball. You know that different conferences have different strengths, okay? How can we determine which conferences have, which conferences are better? So here's like a little depiction of the landscape. And so here we have some of the conferences that these teams are from, okay? So we see Illinois and UCLA are both in the Big Ten. So maybe since they both had good records and there's other teams in this conference that are also good, we could rank their conferences higher. We could boost them a little bit. And then Xavier's down here in the Big East, maybe not doing as well this year. And then you have conferences with teams that you might not know as much about they're not as notorious. And that's usually because they're losing those interconference games, okay? But still, we want to quantify them. Like what is a bad team in the SEC compared to a really good team in the Big East? And how do we quantify all this?
What do you mean by different strengths? I don't know much
Yeah.
about it. So like you're saying within one conference, these people play each other a lot within the conference.
Exactly.
To get to their 22-11, I guess.
Yeah.
And then you're saying that within that conference, there's some data on what the strengths are.
Yeah, so within the conference, it's not too hard to rank who's better than who within the conference.
Oh, yeah.
But then comparing different conferences.
No, I get that, but I'm just saying, like, you are going to then come up with what these strengths are.
Yeah.
how they-
Yeah, we're going to come up with 2 methods to do that. There's plenty of other methods to do it, but we're just going to do 2. And so they're called, one of them is Massey's methods, one of them is the Eigenvector method. And they're lots of fun. I had a great time trying to implement these. So the first one, I'd say it's pretty intuitive. The idea is we're going to assign each team some value that is telling us how many points better than average they are. Okay, and we're going to call that value R sub I. Okay, and so when we have that R sub I and we have 2 teams that are playing each other, we would expect the difference, the score difference between that matchup to be R sub I minus R sub j. And so if people who know ball are saying, oh, these are better conferences up here, those have higher R sub i's, and then the ones down here maybe have negative R sub i's. Okay, we would expect them to be a little bit worse than average. Now, how do we find those R sub i's? We go game by game, and we use linear algebra. So this is our first application of linear algebra. It's lots of fun. I tell my students, like, this is going to be so much fun, like somewhat facetiously, but it ends up being kind of fun. So I have some students in the crowd too, so they could maybe they could confirm. Okay, so let's find these values R sub I, R sub j. So let's go game by game. So here we have Xavier beat Creighton 83 to 61. So that's a 22-point difference. So we would just say Xavier, R sub Creighton is 22. Now we don't know if that means Xavier is 22 and Creighton is 0, or are they 11 and 11, 33 and 11? Like, what is that? That's not enough information, so we do the other games, and we do this for over 6,000 games. And if you were really good at linear algebra, like maybe how Chris was or how Ryan is, I know Ryan's really good at linear algebra, and you recognize that this is a system of equations. And so we could try to solve for R sub I. We'd throw this into matrix vector form. So here we're taking each row, multiplying it by this column of R's, and then we'd see like 1 times Xavier minus 1 Creighton gives us 22, and so on and so forth. If you're an expert at linear algebra, maybe Vicky or Nick or Brian, they're saying, okay, we have a 6,192 by 352 matrix. We're trying to solve this using some linear algebra. Okay, so that's our equation, that's our setup. But if you think about the dimensions, this is probably going to have no solutions. Okay, there's no way you're going to have unique or any values of R sub i's, R sub j's, 352 of them. That's going to give you an exact solution. And so we look for the best solution, something that will minimize the least squares. It's going to be OLS, ordinary least squares. So the errors between our predicted value and the actual value will just minimize this. So this is a regression problem. Yeah. Yeah, teams will play each other more than once, and so when setting up this simple method, I still have to go through a few assumptions. So like if Xavier and Creighton played each other twice, I had that as 2 different rows. Yeah, you could have them cancel out if one team won one game and the other team won the other, or you could just add their scores and have them be one line. But yeah, teams will play each other multiple times, especially within conference. Yeah. So after we've set up that linear algebra, you could solve it using the normal equation, but regression is really easy. Once you get to this point, and it's one line in Python, it's super easy. And then you see what the R values are. Whoever has the highest R value is going to be your best team, and then lowest R value is the worst team. So the question is, how does this work? Right now, all we did is we took 6,000 games, and we looked at the score differences. We didn't look at who the players were and who was home, who was away, when the game was. Was it back in November? Was it 3 weeks ago? This was just using pretty basic stats. And so here are the rankings that arise from this method, and then the R values on the left. And then on the right, we have what the committee actually ranked them. And so I don't want you to go line by line and say, oh, we got the first one wrong, Duke and Auburn, that's incorrect. But look at it in broad strokes. So like the first 2 were actually correct. Duke and Auburn are top 2, and then Houston and Florida are 3rd and 4th. And there are some differences, like they ranked St. John's pretty high. This Massey's method didn't have St. John's in our top 16. But pretty neat that it did a pretty good job of doing somewhat accurate. We have some good teams at the top there. Okay, now we want to see how does this work in terms of the bracket. Like if we were to take Duke and say Duke's going to go all the way, and then Auburn's going to go to until they play Duke, and then Houston is going to go until they play Auburn or Duke, and so on and so forth. So if you put that in a bracket and then count up the scores according to ESPN's counting method, where you assign 10 points for every correct answer on the first round, 20 points for every correct answer in the second round, and so on and so forth, we got to the 68th percentile. Okay, so the chalk just means what would it be if you just use the committee's rankings and had the higher seed win every time. So we didn't quite beat the committee. The committee did a good job this year. When all 4 number 1 seeds make it to the Final Four, that means they did a good job there. So still, we didn't factor in that much information. I thought it's pretty neat that we got decent rankings with some linear algebra and linear regression. Cool. And with each of these methods, there's a fun fact. So with this method, if you really know ball and you follow college football, you know that there used to be a method to find who were the best 2 college football teams because they couldn't have a big tournament. And so the top 2 college football teams would play each other. And to find who the top teams were, they had these computer rankings as one of the factors. And this method, a slightly modified version of this method, was one of the ingredients to those rankings for about 15 years. So
when you say chalk scores, is that what actually happened? Like
no.
Yesterday?
We're assuming Auburn is going to go all the way because the committee put them as the number 1 overall seed.
Got it.
And
what would be assumed?
What would be according to the committee's rankings, yeah. So their predictions according to their rankings. Yeah, cool.
Do you know if they use this Massey for ranking the college basketball teams this year?
I don't know if the current committee uses this. I'm assuming a lot of people use these because Massey makes his ratings public, and it's hard to analyze 6,000 games no matter how many people you have. You want to use some sort of numerics. And so they probably use this, a slightly modified version of this. So we could talk about some of the modifications that we could do to these methods down the line. But you could apply this method to not just sports, but whatever your favorite head-to-head type, all the things we were talking about before, all those dilemmas that we were facing. Cool.
How is this like leveraging like inter-conference or conference strength versus other conferences that might be weaker? Is it doing that or I don't?
Yeah, so going to our conference picture. So it would, through the inter-conference games, through the few times that the Mountain West has played the Big East, and the Big East is going to win more of those games, these will end up more negative. So even though Utah State might be the best in that conference, they might be like -10, and then the other teams are -15. And so the interconference games really help sort these clusters that are the conferences. Yeah. So like when we have a team from the Big Ten or the SEC play a so-called weaker conference, then they're usually winning those games, and that's affecting those R values.
Right, but you don't have an indicator variable indicating, like showing that this belongs to a certain conference.
No, it's not done at the conference level, but that's baked into here. Yeah, it's baked into there. Yeah. Awesome. And so I was actually thinking of calling this talk, if I had to rename it in hindsight, I was going to call it $4 billion algorithms, but that would be probably overselling it. And I also didn't know what I was going to talk about when I signed up to give the talk, and that would have required foresight. But our first $1 billion algorithm is just overall this Massey ranking system for sports betting or for sports rankings. It's a huge industry, and so we'll call that the first one. Cool. All right, time to get a little bit deeper into linear algebra. So that was the first one. Our next method is the Eigenvector method, which there's a lot of versions of this as well. I'd say this one might be not as intuitive, but the way we start is we give everybody 100 points, okay? And then we look at all the teams that a particular team loses to. So in this case, we'll walk through Tennessee. So of these teams, Tennessee lost to Auburn, Florida, and Kentucky. And so we would take Tennessee's 100 points and split it equally between those 3 teams, okay? And we'll do the same thing for all of these teams. So we'll do it for Florida and Kentucky and Alabama. And we'll get something that looks like this. This wasn't all the games, but this is enough games for you to get the idea. Okay, so some teams might have only lost 1 game to everyone else in this little cluster. We really want to do it across the entire season. And so the 100 points are getting divided up over a bunch. I wanted you to think about, like, if you beat a team that didn't lose to that many other teams, you're getting a huge proportion of their points. Okay? And so you could do that once, and that's already a decent version to rank. But so we do that once, and then these would be the points that we're left with. But then you might have teams being like, oh, that's not fair. Like, why did we all start off with 100 points? We beat teams that beat a lot of other teams. Like, we beat the stronger teams, we should be ranked higher. And so you could say, fine, if you want to do that, if you want to consider, say, strength of schedule, like the teams that you beat were really good, then you could redistribute these points. Okay, so now Kentucky lost to 2 teams, so we'll take their 33 points, and we'll give 16.5 to each of those teams. Okay, so you iterate this, and then you have this new distribution. And so you could stop there, and this would give you decent rankings, but since we're math people, we like to take the limit. We say, does this converge? If we just keep on moving these piles of points around, does it eventually converge? And so after one iteration, this is related to win percentage. After a second, it's related to strength of schedule of the teams that you beat. And then when we take the limit, it actually does converge, and there's theorems that guarantee that. So this is one eigenvector method. If you noticed, I heard some people chuckle because I said baby version. If you know ball, who wants to say that they know ball? Does anybody? Okay, Nick knows ball. Nick says, wait, it's not fair to equally split those 100 points or the 33 points between all the teams. Some wins are worth more than others, is what Nick said. So maybe we reweigh those wins based off of how much you won by, right? A 20-point win versus a 2-point win, those aren't really the same. And so instead of splitting equally between the teams that beat you, maybe you redistribute it according to those weights. And so that would be a slightly heavier version, okay? So that second version is the version that I implemented, okay? So that's our non-baby version. Distribute the points based on the score differential. Cool. So let's see. Where's the linear algebra in this? This just looks like a bunch of points moving around. So let's work through the linear algebra because that was in the title. Yeah.
Is there an interpretation when you take the limit? Is there an interpretation there? Because you had one from the first and the second iterations.
I love when people ask the questions that I'm about to get to. It feels like it's planted. My students do this sometime, and I'll be like, bonus point. Yeah. So I don't know if you mean interpretation on the point side or on the linear algebra side.
Probably the point side, but yeah, sure.
We'll go through both. Okay. So when we took those games that we just had and we do this is the baby version where we just have fractions where the way to read this is we're taking this first row, multiplying it by this column. So this is corresponding to the points that Tennessee is going to get. So Tennessee is going to get all of Florida's points and going to get a third of Alabama's points, okay? And then the second line corresponds to Kentucky. Kentucky will get a third of Tennessee's points and no other points, as we saw back in the previous plot. And so we have a matrix times vector, and the linear algebra interpretation, when we repeat this process over and over again, is we're just multiplying this matrix by itself over and over again. We're redistributing those points. And then we take basically a to the infinity, which you could compute without too many issues. A is a 352 by 352 matrix. And so you take its limit. There's this Perron-Frobenius theorem, which guarantees that this limit exists given this setup of redistribution. Not every matrix will have a nice convergent matrix. But in this case, when you impute your values this way, it does. And the eigenvalue is 1. So the interpretation in terms of points is after you keep on shuffling over and over again, it will stabilize. You're not going to have 80 points, 20 points, 80 points, 20 points. It will stabilize to some convergent value. And that's the value where if that was your initial setup, after redistributing it one more time, you're still left with that same point distribution. And so at the end, we have each team has some number of points, and we would just say whoever has the most points wins. right? They're the highest ranked seed, and then whoever has the next most points gets the next most. Cool, so that's the linear algebra behind this method, which if you're paying really close attention, you might see that I relabeled PageRank. So PageRank is the algorithm that Google used for a couple decades to come up with their search algorithm and rank websites. So the idea behind it is instead of dividing the 100 points between teams, here we have 6 different teams. What if we replace teams with websites and we replace defeated with links to? Okay, and we're redistributing points between websites because you want to find which website is the most important, that all the other ones are pointing to it. And so this is a great way to actually rank websites. This is one of the major ingredients within the PageRank algorithm. And this is what I called Google's secret sauce. Okay, there's a lot of other things that matter. You don't want to just like an overall ranking of all the different websites. That's not so useful because when someone searches, you want to specify which websites are relevant. But still, this is one of the major ingredients. And fun fact, when I was first making my first website, a friend who was leading the seminar was like, put a lot of links in your website. It'll boost the ratings and make it more visible. And I think that advice is still given to people, like use a lot of links to get visibility. And I thought about this on the ride here. We actually still do this where if these aren't websites, but these are like maybe people that you're going to follow on Instagram, you don't want to ruin your ratio by following someone without that many followers. So it's funny that like people still use this in their decisions on social media of, oh, I want my profile to be popular. I want to only follow people who are also very popular and have lots of followers. So it's funny that it's like bubbled up to people's behaviors. And fun fact for this algorithm, so Google's PageRank and Eigenvector sorting in general, Eigenvector, what do we call it, ranking. Landau, another number theorist, shout out to Landau, he thought of this way back in 1895 for chess rankings. And so the idea was around for like 100 years, and then Google implemented it, and that's our second $1 billion idea. Awesome. Great. So we got 2 down. We'll get a bonus with the Eigenvector method. So let's go back to our pizza bowl. And okay, we did a pizza poll. We don't actually do a beer poll, but let's just say, hypothetically, we did a beer poll. And now we have some new data, and we got to figure some stuff out. So some things flipped. I'm a little bit stingier with my ratings when it comes to beer. Like, I know what I like, and some of these places didn't have them, so I gave them worse ratings. Francesca maybe just really didn't like those pizza places and is giving better ratings. There's Eric, he's back, and who knows what he's going to give Malt House. But yeah, the ratings changed. And so you might ask, okay, how do we judge the bars that we go to? Well, you could just repeat the same process that we did and get ratings for the bars. Or we don't want to throw out data, right? Maybe we want to combine this data with the pizza data. So I'm going to call this a taste poll, where our first 5 columns are the pizza rankings, and then the next 5 columns are our beer rankings. And so now we're using this data together, okay? Because maybe we could infer some things about individual tastes. Like maybe somebody really likes the ambiance, and they're rating places with high ambiance really well. Or maybe someone likes the bitter taste, and so if the bar has bitter things and the pizza place has bitterness in their pizza, maybe they're rating those highly. And so there's a lot of dimensions there, right? We mostly have been boiling things down to just a single dimension of rating sports teams, but you might have an offense rating, a defense rating. In terms of taste, you might have a lot of different dimensions. If we maybe renamed Taste Poll to Netflix Poll and we put a bunch of shows up there, maybe this will click a little bit more where we have maybe dramas or reality shows or long shows, short shows. So there's a lot of different dimensions. So instead of just projecting down to a one-dimensional thing, this is actually something that Netflix has done where, okay, they don't want to just say what's the best show, but they want to impute these values. They want to say, okay, what about those question marks? Like, is Eric going to like The Glory? if it's supposed to be really high, then we will recommend that to Eric, okay? If this is really high for Francesca, then that's something that will bubble up to really high on Mike Francesca's watch list. Cool. And so they actually ran a contest for this back from 06 to 09. $1 million contest for whoever had the best recommendation algorithm. And this is all behind the collaborative filtering idea, where you don't want to do a full high dimensional space, but you want to find a low rank space. So think something between just a line, a plane, hyperplane. It just captures all the different dimensions that your movie or taste space has. And then when you project your people onto them, whatever the highest values are, you would just rank them. And those are the ones that you would recommend. Cool. Of course, their algorithm is a lot more involved than that. It's not just like basic linear algebra. There's a lot of other factors at play. But this was one of the main ingredients of our third $1 billion algorithm, which is Netflix recommendations. Cool. It's funny that they gave $1 million prize and then made a ton of money off of it. Like, that's such a great business idea of outsource the thinking and then cash in on it. Okay. So you might be like, wait, how did that Eigenvector method do on NCAA? So we look at our rankings, and we circle whoever won, and we actually got the 73rd.4th percentile. So according to ESPN's scoring method, this approach would score 1120. This was the non-baby version, so I did implement the PageRank version, not just the regular old Eigenvector version. And that beats what the committee had ranked. So I'd say that's pretty good given minimal information about these teams, just their scores. Cool. And then anybody who knows ball really well, you probably are all having the same thoughts that any millennial in this room is having. And that's Drake, the Drake meme. Because at the top of this list is Drake. And if you know ball, you'll be like, that's not a good basketball school. How did they end up there? And that's just a fact of how I implemented this method. It was very forgiving towards teams that avenged their losses. Okay, so if Drake lost to a team, which they had 3 losses, and then they played the team again. So here they lost to UIC, University of Illinois Chicago. But they only lost by 4, and then they avenged it, so they won by 17. So the net gain was a positive versus all the teams that they played. And so that's why they bubbled up to the top, and they received everybody's points. So Drake and a few of these other top teams ended up hoarding all the points, basically. Like, they didn't have to give them out because of their net gain. So you could tweak those hyperparameters and get a better ranking system, but this was just a quick and dirty, let's see how it works. Cool. Awesome. So we got 2 applications of linear algebra, also graph theory-ish. Let's turn to non-sports. So best segue ever. We got Drake on the board. Let's talk top 5 musicians of all time. And if you're a millennial, you're thinking, well, we have Dylon. Okay, so instead of top 5 musicians, this is a very subjective thing. Let's talk about top 5 connected musicians, okay, where we want to look at who's collaborating with who, similarly to how we just analyzed teams. So now these are not weighted edges because we're treating all collaborations as equal. Okay, so this data set I found on Kaggle has over 100,000 artists, 300,000 collaborations, so it's a massive data set. This is where my computer started getting mad at me. Just to give you a glimpse of what the data looks like. So I filtered just to see some recognizable names, because there's, of the 156,000 artists, there are a lot who I might not have recognized. So filtering for those who had a popularity score of at least 75. Here's some, where's the names? Dua Lipa, awesome. And then the collaborations is just 2 columns. It doesn't tell you what song they were collaborating on. It was just saying, did they collaborate or not? So it's just this binary variable. Cool. So from this, we could build a graph of, say, this is Jay-Z at the center, and then all the people he has collaborated with, and then all the people that his collaborators have collaborated with, and do some fun network analysis with musicians and their collaborations. Okay, so first I wanted to get a sense of like how popular are these musicians? What is the popularity distribution? Is it similar to basketball where you have maybe a normal distribution of talent? So just looking at popularity frequencies, a lot of people were not that popular in this list, like people that none of us have heard of. So just to give you a sense, of the 100,000, only 12,000 had a rating of at least 50. Okay, so you could come up with cutoffs, and I just said maybe we're going to take the top 50 or the top 60, or you have to have a popularity of at least 70 to make this analysis. And I wanted to do this analysis a lot of different ways just to see what would come out of it. Okay, so if we just did most popular to least popular, that was a quick check that popularity means something, Bad Bunny at the top. It wasn't just the number of followers, so I'm not sure how they computed this popularity value. Okay, so there's different types of centralities that would help you determine how connected somebody is. And so degree centrality is just who has the most collaborators, and PageRank is the one that we did as well. And then we have betweenness centrality, which I wanted to measure, is somebody connecting two different areas, like two different types of clicks? Are they bridging two genres? And so if we're not doing any popularity filter, if we're including all 100,000 musicians, we get Bach up top, traditional. I don't know who Bach was collaborating with. I'm guessing it just has to do with the labels. Like, I'm not sure what's going on. And then we had a lot of DJs, and I tried to do this betweenness centrality, and my computer didn't want to do it, so I had to cut it. So yeah, that was fun. And then I wanted to filter, instead of just saying all 100,000 artists, let's filter everybody has to have a popularity of at least 50. So rerun it. There's still some names. Rehab, I learned, is like this Moroccan DJ, and yeah, definitely learned a lot about some of these international musicians. But still, you could, you can't do betweenness centrality, but you could do a lot of data analysis, a lot of network analysis with a few lines of Python code once you have this graph loaded. Okay, so I did 60, 70, and then you could also filter by genre. So if I just said they have to have hip hop within their genre, we see specific more artists that we recognize, which is cool. All right, so these are only 3 types of centralities when it comes to graph theory. On Wikipedia, there's a list of plenty more. I use NetworkX for all of this analysis, and all of these have their own function. So it's just change one line, and you could come up with your own list, which maybe you want to do closeness centrality, which is measuring the distance from a person to all other people, like 6 degrees of Kevin Bacon type analysis. Cool, and so if you're wondering what is our $4 billion algorithm, so it's actually, it doesn't have to do directly with the music network, but it's the fast Fourier transform, which takes a signal and really, really quickly transforms it into the Fourier transform, discrete Fourier transform. Phenomenal algorithm, probably worth use the most out of these 4 algorithms. And so I wanted to go through the fast Fourier transform, and lucky for us, there's this French paper out there. And so we could walk through this at Malt House maybe, over 20 minutes of beer, as our professor BC Agbula, shout out to BC, as he would say. So that's it for today. These are my references, and I'll hang up and listen. Yeah. Questions? Yeah. Oh, my vibe-based bracket. I didn't rate it here. I was like 26th percentile. I don't know ball. I did so poorly. Yeah, you see a lot of red in there. I got 1 out of the 4 Final Four teams. All my bad code is there on the left if you want to hit that, and if you want to connect on LinkedIn on the right. So, yeah. I will clean up the code a little bit more. It will run right now. It's not that well commented, but I got it up there for y'all. Other questions?
Quick question about the conference distribution. Do we know if like there was like it was equally distributed like inter-conference because that could kind of skew the rank like the rankings?
Like the non-conference games?
Yeah.
No, it's not. That's something that teams sort of organize on their own. So not all teams will have the same amount of non-conference games. That's somewhat left to the individual teams. Yep. So yeah, that might lead to some of the rankings changing, like some of the points going in one direction or another direction. So you do have to make some strong assumptions about the number of teams and number of games that are going on. But if it's like 35 games versus 33 games, I kind of just assume that it would wash away. Yeah.
Would you ever use that method to fill out a bracket?
Yeah, probably next year. It depends on how much ball I end up watching, but next year I think I'll just throw the eigenvector centrality and just that'll be how I enter mine. And then I'll introduce some vibes into it too. Like if UCSB makes it, then I'm going to put them in the Final Four. So, yeah. Thanks.
Time for like 2 questions. Maybe that's... Okay, last chance.
All right.
Really cool overview of playing around this great review, I guess, for me too. Are there any algorithms that you would like to put here based on your forcing function to like learn more like, practically and stuff? Are there ones that kind of identified, you're like, oh, I wish I had time?
So the Netflix one, I wanted to implement RPCA. So it's one of the techniques for data imputation. I really wanted to do that, but I didn't see the right venue for it. And yeah, RPCA is pretty cool. So it assumes that low rank matrix and then projects down to it, and it fills it in. It's like you could imagine what is the best fit matrix. So you impute the mean everywhere, and then you do this iterative procedure to get those values. So I think that's the number one I would want to implement. I've done it in other areas, but not anything that like, that's good for this type of talk. Yeah. Yep.
So I have a question. So for many people, like their rating by some of these metrics, if they're a team or a restaurant or something, might be very important. So do you think there's a way to like design your schedule to like hack your ranking?
So yeah, if you were just doing winning percentage as your ranking, then you're going to schedule against worse teams, and it might be this race to the bottom. For say like Eigenvector, since it's considering the strength of the teams that you're playing, you might not want to schedule, like you want to be evenly matched, because if you're losing, it's going to factor in who you're playing anyways. Like, I don't think you could game it too much. There are some methods where if you play more games, it's really going to benefit you. But for the Massey method that was used in the BCS, there weren't really ways to try to game the system.
So I know I mentioned it because you didn't talk about the
ELO rating. Yeah.
ELO algorithm, but I know like in chess, right? It's used and then it's the cutoff for making certain competitions, and so you get these situations where people are being said to farm ELO, where they go to some place where the players they believe are overrated and they play a lot of games against them, and hopefully get more points. I was just curious if there was like a more sophisticated way to do that that could have.
Yeah. So ELO was one of the ones I was thinking of implementing. It's not as linear algebra-y. ELO is very popular in chess, but you could use it for any sport. And yeah, I'm not sure. That's a good question. That might be a Malthouse discussion. Yeah, great question.
Last chance. I'm glad you asked about is it ELO or LO?
I'm not sure.
Well, I was going to ask about it too, so I'm glad you asked.
I've heard ELO. Yeah.
All right, so one of the two.
ELO is a person. It's not.
Yeah.
Oh, there you go. There's the answer. Thank you. I knew there was someone here who knows.
All right, cool. Thank you very much. All right, do things before we head back. I always do love it when someone mentions the Netflix prize, because a few members of the winning team are members of the Meetup. Yes, they've attended, they've given talks. So I'm very proud of that this Meetup group has turned out some of those winners. So I'm very happy about that. Our pizza ordering algorithm was off this month. So shut the door until everyone finishes the pizza. You know our rule we have. Everyone, if you're hungry, eat a slice. You're not hungry, eat a slice. Take home a box to your friends, okay? So we have plenty of pizza. I hate to see it go to waste. So grab some on your way to the bar and eat some pizza to work up your beer drinking appetite. Like I said, we have May planned for Donna Greenberg talk about AI orchestration. We now have June planned. Thank you very much. All right, Nicole talked to you. We'll figure out a time for you to go. Remember, we are going to Malthouse. Just another show of hands. Who's coming? Show of hands. Who knows how to get there without looking at their map? All right, so you're going to be one of the Pied Pipers. I'll be another Pied Piper, and we'll find our way over there. You know how to get there. Where's your hand? Oh, you raised your hand. Thank you very much. All right, and this month, the members of the Lander team help a lot. Carla is abandoning us and leaving. She's still part of the Lander team, but she's moving to the West Coast. So she won't be here to help out with the meetup anymore. So everyone, thank you very much, Carla, for helping out, doing everything. As she goes to a city that might rain even more than New York does. So, yes. All right, but with that, everyone, good to see you folks, and we'll see you next month. And remember, if you want to see more of these talks, we have like 16 years worth of talks at nyhackr.org. Slideshows, we have videos. We have also at rstats.ai 10 years of the conference talks. So go, use these resources. Go watch the videos, view the slides. They're really good. All right, see you at the bar. See you next month. See you, everybody. Eat the pizza.